Welcome to the Silicon Valley chapter of IEEE Computer Society event. I am the chapter chair, Vishnu Pendyala. Ours is the largest chapter in the Silicon Valley section of IEEE with over 3,500 subscribers in our mailing list and a strong following of over 12,300 on Twitter alone. We are uniquely positioned by the virtue of our location and available expertise. So today, I'll be talking about slowly changing dimensions and fast changing facts, and explain the story of the traditional data warehouse. So most of us are aware of databases, which are quite popular. Any kind of data problem typically is handled using a database. We all know that databases have been around for quite a while now. It has touched our daily lives pretty drastically. But their cousin, data warehouse, serve a different kind of purpose. Databases mostly have been serving, the traditional databases have been serving the transactional needs. But the data warehouse specifically addresses one question. And that question is, how do you generate actionable insights into an organization's performance? So there's a lot of data in the organizations, but the data is useful only if by the way, the meeting is being recorded and also broadcasted live on YouTube. I just wanted to check if all is good. Looks like everything is good. So, so an organization has a lot of data, probably terabytes of data, and executives obviously won't sift through terabytes of data to get actionable insights. They need quick actionable insights. Like how is an example is how is the branch in certain location doing, or how is a salesperson doing in terms of the revenues, or how is the product doing. So these are some of the insights that need to be generated from the data in an organization. So that is the problem that data warehouses solve. So they are mostly informational systems. They serve information, typically for analysis and further action. And the reason they're called warehouse, I'll get to in just a couple of slides. As you know, warehouse is a place where we dump stuff, right? It's a collection of a huge collection of stuff. Typically, the most popular warehouse is the clothes, but there could be other warehouses also. So this specifically is the warehouse for data. So how did it all start? So the content I'm going to present today is mainly attributable to these and other authors. So Inman came up with this building the data warehouse in 1992. So that was the first publication that is quite popular. And then we all know Cod, Edgar Cod. He is the inventor of relational databases. So he and some others wrote a white paper funded by Arbor Software Corporation. I think it goes by a different, some other company acquired it later, so it goes by a different name now. So they wrote a white paper on providing online analytical processing to user analysts, an IT mandate. So that was in 1993. And that's when the term OLAP came into existence. So the term OLAP, online analytical processing, was coined by Cod, and it is quite popular even today. And then, of course, Ralph Kimball, wrote the famous textbook, which is going strong even after all these years. It's called the Data Warehouse Toolkit, the definitive guide to dimensional modeling. So a lot of details are provided in that book. So these can be considered as the pioneering publications in this field, which brought to the fore a lot of concepts about informational data systems. And then running analytics on the data. So an example of a business insight is this. Company ABC made $234,567 from the sale of 13-inch MacBook Pros to customer XYZ. So that's an insight that is pretty useful to the executives to determine customer loyalty and stuff like that, targeting customers and things like that. So how do we generate this business insight? So the first idea that anyone would get is to generate the insights from existing databases, right? You have a bunch of databases in any organization. Databases comprise of tables of data, and so each column is an attribute, and each attribute has a name. So you just tabulate all the data, and using a language called SQL, you will be able to generate insights from existing databases. But what is the problem? So the problem is these databases typically are really rapidly in use. So every microsecond, there are several transactions happening, right? You go to a movie theater or a stock exchange, for example, or any other data-intensive system. The database at the back end keeps getting updated many times in a second, right? So the data is fast changing, and to get a snapshot from these databases, they may have to be locked, right? So that the writes are prevented and we get a consistent snapshot from these data. So that is one way to look at it. But the problem with that is if you lock the database, even for a few seconds, it's going to cause a lot of trouble to the customers, right? You take bank transactions. If the ATM doesn't function, even for a few minutes or few seconds, the word spreads quickly and the bank's reputation goes down, right? So obviously we cannot lock the databases. So one idea that was floated was to typically what we need from the databases are aggregates like this, right? So this is an aggregate of the sales to one particular customer through a number of sales, right? Through a number of purchases made by the customer. So mostly we need aggregates like these for the insights. So the idea then was, why not generate these aggregations during the night when the systems are not busy, and use those aggregates during the day, right? Because most of the executives are working during the day. So why not do the hard work during the night, make the systems do the hard work during the night, store the aggregates in a very efficient data structure, and then use the data during the daytime. So that was the take two. So that was the next idea. So generate the aggregates during the night when the systems are not busy and store them in efficient data structures. In this particular case, it's called the data cube. So a data cube basically stores aggregates. For instance, the data cube here stores the GPAs across 3 subjects: calculus, algebra, topology, and then for multiple students and for multiple years. Probably these are all undergrad students, so their GPAs are being stored, computed and stored. So what are the dimensions of this cube? The first dimension is the subject, calculus, algebra, and topology. The second dimension is the student name, students. And the third dimension is the year, 2015, 16, and 17. So that was the idea. And this concept of a cube can be extended to beyond 3 dimensions, because one of the questions that will come to mind is tables can have multiple columns. And what if there, and each column corresponds to an attribute. So what if there are multiple attributes that need to be captured? So the cube is not really a cube. The data structure is called data cube, but it is not really a cube. It can have any number of dimensions, but still it is called a cube, right? So the idea is to compute the aggregates in these small subcubes, right, or cuboids. So in this case, the aggregate computed is a GPA. So for instance, for calculus, the GPA for NOAA in 2015 is 2. Right. Similarly, for CLO, the GPA for algebra in 2015 is 4, so on and so forth. So this is a very simple example, but you get the idea. So that was the idea of data cube. Now, we already talked about the dimensions of the cube: subjects, student, and year. And the numbers, the aggregates in the subcubes are the GPA. And you can do a number of operations on this data structure. So if you remember data structures and algorithms, algorithms manipulate the data structures, and data structures help make the algorithms efficient, right? So there are a number of operations that can be done. But before that, the aggregates that are stored in these subcubes in data warehouse terminology are called facts. The word fact does not have anything to do with the truthfulness of the number. It just is called fact. It could have been called metric or measure or things like that, but whoever invented the term, they called it fact. So these are all the facts. The 4, 3, 4, all the numbers that are stored in these subcubes are actually facts. So those are the facts, and the dimensions of the cubes are the dimensions. So that's the terminology used in data warehouse. So what are the operations that you can do on a cube? So one of the operations that you could do is to roll up. Roll up is basically eliminating dimensions. For instance, if you roll up to compute the CGPA for a student for a particular year, then we are eliminating the dimension subject, right? So the CGPA is not related to any subject, right? So the CGPA, how is it computed? You sum up the GPAs, individual GPAs, and so that's the cumulative GPA, right? So that is called roll up in data warehouse, a roll up terminology. That's called roll up. So the idea is to reduce one dimension of the cube by computing the sum. So the other operation that is commonly done on cubes is a slice operation. So suppose we want to look at only one student's GPA. Say we want to look at Emily's GPA. Then what we are going to do is we are going to slice the cube so that only this blue subcube or blue subsection of the blue slice of the cube is what we want to examine. So that's why the operation is called a slice. So we want to look at only one particular student's GPA in that case. If that is the requirement, then we just slice. And similarly, there's an operation called dice. And dice is basically selecting a specific range of values for multiple dimensions to create a subcube. An example is just focus on the GPA for Emily. And so that's the slice. And in the slice, focus on a specific time range. For instance, just the last 2 years, 2015 and 2016. So that's what is the dice operation. The next operation is a pivot. I'm pretty sure quite a few of you would have used pivoting. Pivoting in like spreadsheets, Excel spreadsheets. So pivoting is very similar to what we do in Excel spreadsheets. In fact, Excel, when you ask for a pivot in a spreadsheet, Excel at the back end actually computes a data cube and does the pivoting. So, so pivoting is just like an Excel spreadsheet. It involves changing the orientation of the data cube to view it from a different perspective to get new insights. There are other operations also like drill down, which is like roll down. So that's the opposite of roll up. So drill down involves moving from higher level data to lower level data. In other words, disaggregating. For instance, we can drill down from yearly GPA to quarterly GPA. But then the question you might be thinking is, we don't capture the quarterly GPA here. How are we going to drill down? So that is the reason why the grain of the fact, the granularity of the fact really matters in data warehouses and in OLAP, right? So the finer the granularity, the better your capabilities of answering these kind of drill down questions. So now in this case, we don't have the data with us in the data cube. So we will have to go to the original systems, the systems where the data originated to get that detail. So by the way, if you remember, we were trying to capture the data from these kind of databases, the aggregates. So that is the idea of drill down. So basically going to a finer granularity from a coarser granularity. So now let us look at the business insight. So company ABC made $234,567 from the sale of MacBook Pros to customer XYZ. So there is some terminology here. So the number, the dollar amount here, which is the sum of all the sales made to the customer through the sale of MacBook Pros, is, can anyone guess what it's called? It's called the fact. And hopefully, if the business is doing well, if the company is really doing well, it should be fast changing. right? If today it is $234,567, tomorrow it should be probably $240,000. Hopefully, a few more employees of that customer may have purchased MacBook Pros, ordered MacBook Pros, and it goes up. So that is where the fast changing fact is coming from. So the hope is that the facts that you store in the aggregates, store in the cuboids or subcubes, or for that matter, we are going to talk about data warehouse, the traditional data warehouse. So the hope is that the facts which are captured in these data structures are fast changing. That's why they are called fast changing facts. Now, what are these? 13-inch MacBook Pro, customer XYZ. So I'm trying to break the suspense here. I mean, the title was fast changing facts and slow changing dimensions. So there was a deliberate intention of choosing that title because it's a bit curious. It makes one curious. What are fast changing facts and slow changing dimensions? So these are facts, and now these obviously should be the dimensions. So those would be the dimensions of the cube. I mean, it's not really the cube all the time, but the terminology still holds. They're called the dimensions. By the way, whether it is machine learning or data warehouse, the columns in the table, in a table like this, are called dimensions. So title is a dimension, author is a dimension, so on. So the same terminology applies to machine learning as well. So now 13-inch MacBook Pro and customer XYZ are called dimensions. And hopefully they are slowly changing, because if you dump too many changes on the customers, for instance, today it is 13-inch MacBook Pro, tomorrow the release is 17-inch MacBook Pro, the customers will get disenchanted, right? I mean, you would lose customers if you change your products that often, particularly if they are not backward compatible and things like that, right? So hopefully the dimension should be slowly changing. It should not change too often. That's why they are called slowly changing dimensions. So dimensions capture the context for the facts. So when you store 234,567 in the data cube, the subcube, the context for this number comes from the dimensions. So one dimension is the product and the other dimension is the customer in this case. So facts capture measurable data like sales, revenue, quantity, and so on and so forth, whereas dimensions capture the context. So descriptive data like time, geography, product, and so on and so forth. So that's it. That's the essence behind fast changing facts and slow changing dimensions. Now, what is the problem with this data cube approach? What is the problem in capturing the aggregates during the night from the transactional systems, databases, and then store them in the data cubes? There is still a problem. First thing is, not all data is sitting in databases, right? In a typical organization, you have data in spreadsheets, you have data in file systems, you have data in all sorts of places, right? So you need to be able to collect data not just from the databases, but from all these diverse platforms. In fact, in the modern day, because of the big data, the 4 V's of big data are velocity, variety, volume, and veracity, right? So because of the variety and volume, this is an even more important problem, because the data does not only sit as spreadsheets and files, but it could sit in the form of images, in the form of audio, in the form of video, so on and so forth. So that's a different topic. Dealing with the big data is a slightly different topic. we use what are called as data lakes and things like that. There are newer concepts coming up. But the original concept of data warehouse is still going strong. So there is a need to extract the data from these disparate sources of information, transform the data to fit a uniform way of storing data, and then load that transformed data into the actual data structures like data cube. And in the next slide, I'm going to talk about a different kind of data structure, which is, of course, our well-known RDBMS. So there is a need for what is called as ETL, extract, transform, and load the data into these data structures. So that is one problem. And the other problem is there is a need to preserve historical data with specific need to find temporal patterns. So what does an insight, useful insight, comprise of? It comprises of patterns. The insight that we saw here was a very simple insight, but typically to make decisions, for the executives to make decisions, you really need to capture the historical data. How is a product doing over subsequent quarters, consecutive quarters? So Q1, Q2, Q3, how is the product doing? How is the salesperson doing? How is the store doing? So most of the business decisions are made on historical data. So we need to be able to capture historical data, which could typically run into billions of rows, depending on how soon and at what granularity you're capturing the data. It could run into billions and billions of rows. So obviously we can't use a transactional system, which is the backend for, say, movie ticket sales or stock market exchanges, stock exchanges, and so on and so forth, or for that matter, even banks. So we cannot burden the transactional systems with this kind of historical data. And then the other problem is, so what we thought was we could use the systems during the night, but these days of globalization and different time zones and all that stuff, there's no night time, right? For banks, or for instance, Citibank. Citibank has branches all over the world. Most of the countries have Citibank branches. So there's no night for Citibank, right? So the performance does not really scale as analytical processing needs grow, right? So when the operations grow, the informational needs will also grow. And when the informational needs grow, you cannot burden the transactional systems with this need. So need for analytical data, insights. So obviously transaction processing takes precedence, and it cannot take a hit because they are directly interfacing with the customers. So slowly the need for a separate system is arising, as you can see. And the other thing with transactional systems is there is a concept called normalization. So normalization, the essence of normalization, or the key idea behind normalization, is each table should store the data pertaining to a single theme. For instance, customer is one theme, and product is another theme. We cannot store both the data belonging to customer and the product in a single table. That will cause problems and anomalies, what are called as anomalies in the database parlance. So that is the reason why they have to be broken up. And the process of breaking up tables to just focus on a single theme is called normalization. So there's a whole theory of normalization, which is quite interesting. So so in a typical data analytics database using databases course, we first talk a lot about normalization. So we learn a lot about normalization. And then when we talk about data warehouses, we unlearn that. The reason is, if there are too many tables, if you keep breaking the tables, if there are too many tables, to get information from those tables, you have to hop a number of tables. So those hops are very expensive in databases. So normalization can come in the way of efficient analytical query processing. We want a much simpler structure for our database. We don't want to hop across multiple tables. Hopping is basically doing a join in SQL. What is called SQL is a query language for databases. So we don't want to do these joins. So we need a different way to model data for data warehouses. So the performance needs, the performance impact requires a separate database. The data modeling in terms of normalization requires a separate, forces us to use a separate system, and so on and so forth. And the needs are also the needs that the transactional processing systems and analytical processing systems serve are also totally different. So the conclusion is that we cannot mix OLTP systems with OLAP systems. Online transactional processing systems are operational, and online analytical processing systems are informational. The needs are different, the processing requirements are different, the data models are different, the performance needs are different, the query structure is different. So there's a whole, that's the reason why we have to study data warehouses separately from databases, right? So the solution is to come up with a simpler data model, which is kind of denormalized. So that means some of these tables could contain multiple themes. Because the reason again is that we don't want to do multiple hops. So the star schema, as the name indicates, is a very simple schema. So there is a single table called the fact table at the center. And surrounding the fact table are the dimension tables. So these are the dimensions of the cube that we saw, right? And the facts capture what we store in the subcubes in the data cube. So what we do is we perform extract, transform, and load operations, ETL operations as they are called, from many disparate sources, and periodically refresh the data, load the data into these tables. We obviously have to adopt a denormalized way to store data because we don't want too many tables to hop. So the fact table contains historical snapshots of the data, just like the subcubes in the cuboid. And the other thing about fact table is that it contains historical snapshots. So what does that mean? It means it could have billions of rows, right? So it's a very long table. Because the table is very long, running into billions of rows, the table has to be lean as well. That means the number of columns. So each of these rows actually is a column in the real table. So what are the columns? So first set of columns, I'll start from the bottom. The first set of columns are the facts or the metrics or the measures. Some of the measures that are captured here are quantity sold, amount sold, average sales. Okay, this is a very simple example, but you get the idea, just to give you an idea. So these are the facts that are stored in the fact table. We typically don't store a whole lot of facts, just a few important facts. So the aggregates, these are all the aggregates, if you have noticed. Quantity, average, and all that, these are all aggregates. So that is one class of columns in the fact table. And the other class of columns are the foreign keys. FK is a foreign key. So these are the keys to the tables around the fact table, the dimension tables. So for instance, so item key is the primary key which identifies a particular row, particular item in this item table. So we store the primary key of the item table as a foreign key in the fact table. Similarly, the time of the sales or whatever. So typically there's a time dimension table, which is almost invariably there in data warehouses. Any data warehouse you take, there's a time dimension. There's a strong reason for it because we are capturing historical data. For instance, the executives want to know, how did the Thanksgiving sales go? How were the Thanksgiving sales? Now, we cannot write queries to determine when the Thanksgiving day was and all that stuff, right? So all that information, the special days information is captured in the time dimension or the time table. So time is a dimension table, and such special information is captured there. So there is it obviously every row in a table needs to have a primary key. So that primary key is what goes into the fact table. Similarly, branch ID refers to which branch the product was sold. So, and then location. So you get the idea, right? So each row in this table will tell you the quantity sold, the amount sold, and the average sales by the item, by a time frame, by a branch, and by location. That is what each row means. So you get the facts from the fact table, the measures or the metrics from the aggregates from the fact table, and the context for that aggregate from the dimension tables. How do you do that? You do a join on this item key, time ID, branch ID, and so on and so forth. So that's how you get the information from the dimensions, right? So that is the idea of the star schema. Now, just because star schema is available, it's again an RDBMS. It's a relational database management system. It's the only difference is that it's much simpler, and there's a particular way in which the tables are organized. And the particular way the columns are selected. So just because we have the star schema doesn't mean that we can throw out our data cube, right? That we talked earlier. So data cubes are typically used as a front end for the star schema or a data warehouse. So we still can get aggregates from the star schema into the data cube, and we can do slicing, dicing, and all those good operations, the pivoting and all that stuff on the data cube to get more insights, right? So data cube is not going anywhere. It is still in popular use. By the way, I think the paper which proposed data cubes is one of the highly cited papers in software. So it's a very, but the concept itself is very simple, very intuitive to understand, but its utility is really huge. So now let's take an example of sales. So this is the fact table. So we are capturing the quantity sold and the amount as the facts, as the measures or the metrics or the aggregates in this table. And just like before, we are going to save the foreign keys for the product table, time table. These are all dimensions: time dimension table, location dimension table, branch dimension table, and so on and so forth. Of course, here there are only 1, 2, 3, 4 dimensions. So we are this product with an ID 101 during this time frame with ID 1 with this location and this branch, 5 items were sold for an amount of $150. That's what we are capturing the fact table. So facts are fast changing, right? So facts tables, therefore the fact tables are very long. Remember, if the facts are not fast changing, what does it mean? It means the company is not doing well, or the company is not dynamic enough. So facts are typically fast changing. That implies that we have billions and billions of rows. So they are very long. And therefore, the fact tables need to be lean also. Why should they be lean? Because the storage considerations, right? The disk IO is very expensive. So we want to reduce the disk IO. So we want to minimize the number of things that we are going to store in the fact table. So that's the reason why they're lean and long. Fact tables are lean and long. And typically fact tables contain only numbers, no strings, no characters. Because if you look at the fact table here, you see only numbers, because the ID is a number typically, which is a foreign key to the dimension table, and then the measures or the metrics are numbers as well. So fact table contains only numbers. Now, on the other hand, dimensions are very descriptive. They are all characters, strings, maybe some numbers, but mostly strings and characters. And they're wide. Why are they wide? Because we don't normalize typically, particularly in the star schema, we don't normalize. So they are wide and short, right? Because take for instance, the product dimension. So how many products would be there? Certainly not billions, right? Take, for instance, customers. How many customers? Maybe a few thousands, not billions, certainly. So dimensions are typically short. So they are short and stout, whereas fact tables are lean and long. So isn't that interesting as well? So mostly contain strings, and they provide the context for the facts stored in the fact table. That is the purpose of dimension tables. So let us look at some of the examples of the dimensions. So in this case, every row in the time dimension table. So dimension, we typically drop the word table. We just say dimension because it is understood that dimension means a table in data warehouses. So anyway, to be clear, I will use dimension table. So the time dimension table, each row in this case happens to be a single day, which contains a date and the day name. So single day, but this is not usually the case. Time dimension table is pretty exhaustive. It captures a lot of information, but just to explain the concepts of data warehouse, I just chose an easy one. So each day is a row in the time dimension table. And location similarly has an ID and a name. Then product has product ID. This is if you have been noticing, the first column is the primary key, which identifies the row in that particular table, right? So just the primary key and the location name. Again, this is a very simple example. The real world applications contain many more columns. So product, similarly, there's also a category ID. If you have noticed, category could have been a separate table in itself if we normalize. But in this case, we club both product and category. And then the branch is another dimension table. So those are the dimension tables and just one fact table. Now, how do we generate insights business insights from this kind of a architecture or this kind of an arrangement of the tables. So an insight that we want to generate here is what are the total sales amount for each product in city A during the month of May 2023. So we just write a SQL query, because remember, these are all relational tables. Table is a relation, basically. The math concept of a relation, right? In the set theory, there's something called relation. So a table is essentially a relation. That's why it's called relational database management system. So the data warehouse is basically a set of relations or tables. So we use SQL, just like we use SQL in RDBMS, we use SQL. So we want the product name, the sum of the amount. So we want to sum up the amount. This is the aggregate that we are interested in, total sales, right? As the total sales amount. This is an alias for sum, right? If you know SQL, you will recognize this as an alias for sum. From sales S, the table S, which is the fact table here. And then for the description or the context for this aggregate sales amount, we want to join with the dimension tables, join on the dimension tables. So product is one dimension, location is another dimension, time is a third dimension. And how are we going to join? We are going to specify the conditions in the query. Location name. Sorry, the joins are based on the primary key and foreign key. So we want the product, the foreign key stored in the fact table to match the primary key stored in the dimension table for product. Similarly, the foreign key stored in the fact table S should match the primary key for the location dimension table. So that's how we are going to join. And similarly, time. And then we condition on whatever is specified in the query. In this case, we are interested only in city A. So that's what we are going to specify, and only for the month of May. So we specify the date between 1st of May and 31st of May. And then we are going to group by product name. So that is how we generate insights from a data warehouse in star schema. Now, star schema is the most popular still, but there is also the snowflake schema. What is a snowflake schema? And why is it called snowflake? So the reason is because it looks like a snowflake. If you have noticed, the star schema looks like a star, right? So there's something in the center, and then, I mean, they could have called it like hub and spokes and things like that, but they call it star because it looks like a star. So the snowflake schema, as the name indicates, looks like a snowflake. So there's still a table at the center, which is the fact table, of course, and there are still dimensions surrounding the fact table. But then there are other tables which connect to the dimensions. So what are those tables and how do you get them? Remember, we talked about normalization, right? When we normalize the dimensions, they result in single themed tables. That means we are going to break the table into multiple tables. That means we need to do multiple hops. So it is sometimes useful to normalize the dimensions, and that's what results in a snowflake schema like this one. So you still have the fact table at the center, the dimension table surrounding it, but then the dimension tables would be broken down. So if there are multiple themes like product and customer in the same dimension, we are going to break them down. So, or the other example is product and category in the same dimension, you are going to break them down. So product as one table and category as one table. And we obviously storing the primary keys for all these tables in the fact table will make fact table stout or wide, which is a no-no because it contains billions of rows. You cannot store, the table cannot be fat. So we want lean and long fact tables. So that is the reason why we just do joins, right? So we do a join with this dimension and this dimension and so on and so forth. So that is the idea of a snowflake schema. So the next topic I wanted to briefly cover is dimensional modeling. So how do we come up with the star schema or snowflake schema? What are the considerations and things like that? So the key considerations are what are the dimensions and how many of them? How many dimensions do you want and what are the dimensions? So the goal is to minimize the storage. Why? Because disk I/O is very expensive, right? So we want to minimize the storage, disk storage. So that is one of the key considerations. And the other consideration is what numeric quantities will be stored in the fact table. What measures do you want to store? What metrics, what aggregates do you want to store? Do you want to store the GPA, quarterly GPA, or do you want to store the annual GPA, or at what level of granularity do you want to store? So Ralph Kimball and others recommend using the smallest grain possible, because if we store a coarser grain, then we cannot drill down below the grain of the fact table, right? So if you want finer details and we store only coarser details in the fact table, then it becomes difficult to drill down. So that's why experts suggest that use the smallest grain possible. So that's the granularity part of it. So finer grain implies better detail for drilling down, but more rows. So here's an example. Suppose there are 60 dimensional attributes and 3 facts to be captured in the fact table. So just like before, we just have 3 facts, but there are 60 attributes which provide the context for these 3 facts. Now, how do we design the star schema? So how many dimension tables should we have? So there are 3 major options. So we can have 1 dimension with all 60 attributes. We can have each attribute, we can make each attribute get its own dimension table. That means 60 dimension tables surrounding the fact table. Or we could have just 4 dimension tables with probably around 15 attributes, storing around 15 attributes in each table. So which one do you think works the best? So the first option is 1 dimension with all 60 attributes. So we have 1 fact table, 3 facts, and because we have only 1 dimension table, we have only 1 foreign key. And the dimension table will have 60 attributes. So which table is fatter or wider? Obviously, the one with 60 attributes, right? The dimension table is wider. And which one is longer? Interestingly, both the tables will have same number of rows, because one of the attributes could be date. And if we are capturing it by the date, then there are as many rows in the dimension table as there are facts. So that means huge storage is needed for this option. Second option is each attribute gets its own dimension table. So that means there are 3 facts just like before, but there will be 60 foreign keys to 60 dimension tables. So there will be 60 dimension tables, each capturing 1 attribute. So which table is wider? Neither is wider, right? I mean, these tables are also small, not wide, and these probably the fact table is wider, right? Because you are capturing 60 foreign keys. Even if you consider 4-byte keys, we are talking about 60 into 4 is like 240 bytes just for the foreign keys, and then billions of those. So this also is an expensive option. And which table is longer? Obviously the fact table. The dimension tables will be very short. The storage needed for the dimension tables will be negligible, right? So the third option is bunch correlated attributes like product name and category together. And then just have 4 dimensions. Probably each dimension capturing around 15 attributes. So then we'll have 4 dimension tables and 1 fact table with 4 foreign keys. So remember, we need to bunch only correlated attributes like product name and category. Otherwise, if we bunch uncorrelated attributes, there will be too many rows of combinations, right? If there are too many rows of unique combinations, it will result in long dimension tables and lots of storage needs. So that's why we obviously rejected option A, right? So those are the 3 options. Now, which one fares best? Option A is the worst because the dimension can have as many rows as a fact table, and that's a disaster, right? Huge storage. Option B, dimensions occupy less storage because the tables are really small, right? They're really small, just 1 attribute in each table. But the fact tables will be very wide. 60, right? We talked about 60 for fact table, 60 dimension tables, so 60 foreign keys, right? So that is option B. So it occupies less storage than option A, probably, but it is still huge. So option B is slightly better than A, but certainly not the best, probably. Option C is the best because it's quite intuitive, right? There's a nice balance between the fact table size and the dimension arrangement of the dimensions. So that is the reason why typically this kind of configuration is more accepted. Okay, so that's about the dimensional modeling. Now let's talk about slowly changing dimensions. So we know the dimensions have to change slowly. If they change fast, I mean, there could be cases when the dimensions could change fast. We'll see how to handle those, but typically they should change slowly. For instance, take the example of a customer. How fast does the information about a customer change? How often does the name of a customer change? Very rarely, right? If at all. How fast does an address change? That also very rarely. So the dimensions change very slowly. Now, how do we handle rarely occurring changes to dimensions? So the first option is the ostrich algorithm. So in computer science, the ostrich algorithm is quite popular, right? So the ostrich algorithm is just stick the head in the sand and do nothing, right? So ignore the changes. So that is called type 0. Sometimes this is good enough for us, but typically not. So the other option is to overwrite the existing values. So erase the history, right? You overwrite the history and create new data. That is type 1. So that's called type 1. The other types find ways to preserve the history. So type 2, type 3, type 4, type 5, they're all try to preserve the history. So let's look at type 1. Type 0 is, of course, do nothing, but type 1 is in place update. So for instance, let the customer, we want to incorporate changes to the customer dimension. So let the initial customer dimension be this. right? So the customer ID is there. We are capturing only two customers, 101 and 102, John Smith and Jane Doe. So they are in New York and Los Angeles respectively, and the loyalty status is gold and silver. So that is the initial customer dimension. Now there's a change to the customer information. What is the change? The change is that John Smith moved from New York to Boston, and his loyalty status changed from gold to platinum. So how do we take care of this? We just override the values. So in place of gold, we are going to write platinum. In place of New York, we are going to store Boston. So slowly changing dimension, SCD type 1 is straightforward and efficient. But it is not suitable for scenarios where we need to track historical changes, right? We need historical changes for analysis or auditing purposes, right? So for that, we need to use other SCD types like type 2, type 3, and so on. So what is type 2? So type 2, historical tracking. Once again, the same change has come in, but the way we handle this change is different now. What we are going to do is we are going to create a new record. So a new record is added for the customer with ID 101 to reflect the updated loyalty status. So, in this case, there's only one change, which is the loyalty status. The city does not change. So we just save. So the original role remains like that, no change. The second row contains the change. You will also notice that there are a couple of columns added as well. So the effective date and end date are also have to be stored along with the information. So we assign an end date to the previous row where the loyalty status was gold. And effective date for the new row will be the date when it got changed. So that is the idea of type 2. So we need to create a new row. So the new record has a start date or the effective date when the updated data becomes effective, and the end date of the new record is left as null to indicate that it's the latest version. So if the end date is null, it means it's still valid. So that is type 2. So type 3 is called alternate reality. This is used relatively infrequently. So here again, the status is changing to platinum. That's the only change. Now, what we are going to do here is we are going to create a new column. Instead of a new row, we are going to create a new column. So the loyalty status field is updated to the new value, which is platinum. But this new column called previous loyalty status is added and updated to retain the previous loyalty status, gold. So, but the disadvantage with this is, suppose there are multiple changes, then there's no history beyond the previous value. So we are saving only one previous history, one previous state, not multiple previous states. So that is one downside with this. So this type is typically appropriate when we only need to track specific changes and a limited history, only the alternate reality, just one state. So that is type 3. So type 4 is when the dimension is rapidly changing. For instance, in this case, the loyalty status is changing rapidly. So maybe is his buying pattern, John Smith's buying patterns are changing rapidly, and therefore we create a new dimension. So yeah, new table. So we create a new table for the loyalty status. Whichever dimension, whichever attribute has been changing rapidly, we create a new table for that. We call it loyalty status. So the original table is now split into two tables. So the loyalty status goes into a second table. And then you have the start date and the end date for the loyalty status. So we update only the mini dimension. We don't touch this main dimension, but we keep updating this mini dimension. So the start date and end date mean just like before. So the advantage of type 4 is that it allows us to maintain a separate dimension to capture changes in specific attributes over time without burdening the main dimension table. So this approach helps us maintain a clear and detailed history of changes without altering the main customer dimension. So it is particularly useful when we need to track specific changes for certain attributes which could change often. So that is type 4. So there are many other type SCD types. There are hybrid approaches. For instance, type 5 adds a mini dimension. So it is type 4 plus type 1. So type 5 is basically 4 plus 1. You can see 4 plus 1 is 5. So that's why type 5 is type 4 plus type 1. Similarly, type 6 is type 1 plus type 2 plus type 3. You do all three types, you get type 6. So on and so forth. So that is the story of the traditional data warehouse and the fast changing facts and slowly changing dimensions. So if you have any questions, I'll be happy to take, or I am available online. You can contact me. I have a website and I have quite a substantial presence on the social media, so you can connect with me. So any questions? Let me check the YouTube. There are no questions on the YouTube. Neither are there any questions on Zoom, so we are all good.
Vishnu?
Yeah, hi.
Can you hear? Hi. So one of the things that I wanted to know is this an active area of research? In other words, have you given us sort of like the end of the line understanding of this, or is there still a lot of activity going on in this space?
So there is still a lot of activity going on in the space. This is just the beginning. So
okay.
Yeah, this is just the beginning.
Because it all seems to me that what people are exploring is variations on data compression that allows us to do optimized signal processing. And so, there are various ways of how do I make the main run work well so I can get a current understanding of the present. And at the same time, if I want to drill down, I can find out some detail that would otherwise clog the main data run.
Yeah, so compression is typically used in columnar databases, which are quite used for data warehouse. So that is also an area of research. So yeah, there is a lot going on in this area. But I just wanted to, for those who are uninitiated, I just wanted to start.
Sure. So the last thing is you've mentioned disk drive several times in your talk. How do you expect this to change as we move to a more solid state disk world?
So there are some in-memory databases as well, which really speed up operations.
Mm-hmm.
So that is also one area of research. So there's a lot going on in this area.
Okay. We just had Flash Memory Summit, and nobody talked about this topic as a main topic, but it sounds like every company has something like this. So it seemed to me that Flash may make a tremendous difference for those customers.
Yeah, certainly. But the problem with flash memories is that there's a limitation on the amount of storage, right? And these data warehouses typically run into terabytes or petabytes. So that makes it a challenge. But if there's a smaller scale data warehouse, typically they're called data marts. So probably flash memory might be considered for those.
Okay, good to know. So smaller companies may have an advantage using these techniques to track their business. It's going 24/7 can actually be costly from an IT point of view.
Yeah, that's right. That's
okay.
Yes.
Thank you.
Thank you. Thanks for the questions. Okay, with that, we come to the conclusion of the session. Thank you all for joining. And I hope to see you in our next month's event, which will be in person. Sorry. So September 5th, we have an event which will be in person. Hope to see at least some of you there. Thanks.